Okay, so I'm basically taking this lecture, and Professor Ruina would be here on Thursday. He had a medical appointment today, so he couldn't make it to class today. So what I'm going to do today is this. Just tell a few things about the problem which we did in class last time, and finally I'll start with collisions in 2D. Okay, this is chapter 11 in the book. Okay, so the problem which Professor Ruina discussed in class last time was a particle M2 moving around particle M1 attracted by the so-called gravitational force, and he set up the free body diagram for the mass M2. So if I'm not loud enough, please shout out and say I'm not loud enough. If you have questions during any part of the lecture, just raise your hands or shout out the question, and I'll try my best to answer it. Okay? So that's M2, and this M2 is acted upon by force F because it moves around M1, and so the free body so that's the free body diagram, and we use Newton's laws. So let's say the linear momentum balance is F equals L dot, and F here is M2 A, and that should be equal to, sorry, so F is the external force. So the external force here is not M2A. So L dot is M2A, and the external force here is minus G M1 M2 divided by R square. I'm running out of space. R2 squared, and since I have a vector on the right hand side, I need to multiply this by unit vector, which means that magnitude of R2, or this can be rewritten as R2 cubed. And so you can take this equation, and with this equation, V2 equals R dot, R2 dot, and of course A2 is given by V2 dot. You can take these two equations, put it in MATLAB, and try to plot or try to see how M2 moves with respect to M1. And that's what we did in class last time. So here R2 is xi plus yj, and V2 is V2xi plus V2 by j. Okay, so let's see if let's look at the angular momentum of the system. So the angular momentum AM is also given by this letter h, and that's a vector, so I put a vector sign, and the angular momentum is typically about a certain point. So let's say we want to find the angular momentum about point A. That's simply R2 crossed with M2 V2. Okay, let's see what if we write an equation similar to the LMB, which is this is called AMB, that is, so this is F equals MA, this is similar to torque equals I alpha, and that is written as rate of change of angular momentum is equal to the external torque acting on the system. Very, very similar to this equation, right? So what are the external torques on the system? Well, the external torque is only due to the force F, which is pulling this mass closer, and so remember this is a moment, so I have to do R cross F. But what is the force? The force is minus g m1 m2 r cube times r2. But can you tell me what this quantity is? I have a scalar times, the magnitude of f times r2. That is crossed with r2. R2 cross r2 is just 0, right? So this is 0, which means that h dot a is 0. So if h dot a is 0, that means h of a is a constant. Which means that this quantity is a constant. So R2 crossed with M2 V2 is a constant. Well, I'll just try to simplify this. R2 is xi plus yj crossed with M2 V2 xi plus V2 yj, and this can be rewritten as, so I can take cross of this with this, that's going to be 0 because I cross I is 0, xi with this I cross j will be k, so x times v2y along k, and then this times this is simply y times v2x times j cross I is minus k, so this is going to be minus k, and that with v2y is going to be simply 0 because j cross j is 0. So let me rewrite this. Okay, so my calculation says that this should be a constant, which means that this quantity x v2y minus y v2x should be a constant, right? Okay, so why am I doing this? Well, it turns out that Professor Ruina showed you a simulation of this body moving around M1. One way to check your code is to verify if this quantity which I've derived over here is actually a constant. In your simulation, if you figure out that this quantity is not a constant, it means that you made a mistake somewhere. Okay? That's one quantity which is conserved. There's another quantity, there's the energy which is conserved. So I'll try to write the total energy of the system. So if I do that, remember that this particular system, in this system, the force is only a function of r. And when the force is only a function of r, there's a potential associated with that field, right? So the potential, so the rate of change of potential with respect to r is minus f r, then you can find that potential. So let's try to find that potential. Equals g. So this is a wrong equation here. I have a scalar equating to a vector. So that's more appropriate. Okay, so that is g m1 m2 divided by r squared. And since I have a negative sign there already in the force, that should be true. And so let's try to integrate this. PR, and let's see. So the potential at infinity, let's assume that's equal to 0. And the potential at some distance r is EP. So if you carry out the integration, what you find is, what you get is g m1 m2, let me just do it, minus r, upper limit is is R, and the lower limit is infinity. And so what you get is EP equals minus G M1 M2 divided by R. Should be positive. So okay, let's see. So you agree with this? Agree with this? So the integral of 1 over r square is negative 1 over r. So the negative stays, I think. Am I doing something wrong? So integral r n dr is n plus 1. So minus q plus 1. Okay, so that's the potential. So let's try to find what the total energy is. So ET is EK plus EP, and EK is half mv square, and the potential here is minus G m2 m1 m2 divided by r square. Sorry, r. And we know that for this system, all the forces are conservative. There's no dissipation whatsoever, which means that this term here is a constant. So let's just simplify that. So I'm going to rewrite this in terms of x's and bx's. So this gives me half m2 bx square plus by square minus g m1 m2 divided by x2 square plus y2 square. That's a constant. Okay, so there are two things here. One thing is one thing is the angular momentum is conserved, which means that this quantity in my simulation should work out to be a constant, and the energy is also conserved, which means that this quantity also should be a constant. So let's see if that's true in the simulation. So so what I did was I wrote down these two. So in the code which Professor Ruina posted on Blackboard, he had not put these two things inside the code. I just put those things down, and let's just check if they are indeed constants. So the code is very much the same, except that I added these lines. So I write the velocity, I write the position, I try to find what the angular momentum is, what the total energy is, and so I'm going to plot that on figure 3 and figure 4. So you're looking at figure 3 and figure 4 once I run the simulation. Show it on the other screen. I have to move it here. That's figure 4. And okay. Okay, so what you see here on this figure is angular momentum, which is time, and you see that the angular momentum is actually increasing, right? But the increase is pretty small. It's like 5 parts in 1,000. This goes from 1 to 1.005. So 5 parts in 1,000 over 7 seconds, and the energy I think is also about 5 parts in 1,000. Now what if I increase the number of steps? So I'm going to make my simulations more accurate by putting another 0 here. So more time steps, which means that Euler's method will be more accurate. Takes a while. Okay. So now you see that the energy is more like, so this is 1, that's 1.005, which means that we are like 5 parts, we are inaccurate by 5 parts in 10,000. Similarly here, I think it's about 5 parts in 10,000. So you see that as you increase you make the grid smaller and smaller, that is by increasing n, you see that your solution becomes more and more accurate. And in this case, you can use these two things, these two numbers in this case, angular momentum energy, to check if your code, to debug your code, to see if you have not made any mistakes. Okay, so sometimes you do not know the solutions to the problem. Like in this case, you knew that the motion would be like a ellipse or a circle, but what if you did not know that was the solution to the problem? Then sometimes in some special problems like this one, when energy is conserved, we can use energy, and angular momentum is always conserved for all systems, so you can use that. Okay? Any questions? Yo, blank. Okay, so moving on, let's go to collisions in 2 dimensions. So the setup is collisions in 2D. Okay, so the setup is there are two masses. Let's call them M1, M2, traveling with speeds v1, v2. Now we are in 2D, so I'm going to write everything in vector notation. Let's call the speed of mass M1 as v1 and that of M2 as v2. So this is P4 collision. I'm going to use negative sign to indicate time before collision. Then what happens is these two particles collide. So M2, M1, and then afterwards they go on their own path. So M1 say is going this way, and M2 is going that way. And all are vectors. So if you call this after collision, this is during collision, and if you make a plot of the force versus time before collision, the interaction force is 0. Then during collision, what happens is the force is a big spike, and then it is 0 again. So that is so there'll be a huge, rather large force acting between the masses during collision, and so that's before and that's after. So even though the force is sort of infinite, this goes to infinity, the impulse is finite. So the quantity which we'll use to quantify collisions is to understand collisions as impulse. So impulse is defined as the first integral of force. So let P denote the impulse, and the impulse is given by the integral f dt. Okay, so this is infinite, however this is finite. Okay, this is called an impulse. This is the collision force. Okay, so we have that. Now the question is, can we do useful mechanics with what I have over here on the board? Well, it turns out you can. So what happens is, let's draw a free body diagram for the system. So the free body diagram now is going to be, I'm going to draw the free body diagram for this instant when the collision is taking place. So during collision, what I would have is a force P, an impulse P acting on mass m2, and the same impulse should act on mass m1 and would have a opposite direction with the same magnitude. Because the question is, what is P? So P is integral f dt, and you can write f as ma, so m2 a2 dt, and a2 dt can be rewritten as dv2 dt dt, right? And you can rewrite this as m2 dv2. And once you have it in this form, I can just calculate what the impulse is. So let's carry out that integration. Okay, so P is that integral, and that integral goes from V, so V1, so V2 negative to V2 positive, as I have it over here. So that's going to give me M2 V2 positive minus V2 negative. Now you can do the same calculation for this mass, carry a similar procedure, and find, and what you'll get is minus P equals M1 V1 positive minus V1 negative. Okay, so what is the impulse? This is the impulse, and how do you calculate it? If you know the velocities before collision and velocities after collision, then you can find what the impulse is. Okay, so let's see. So in this particular scenario, what typically happens is you typically know what these velocities are, and you do not know what the velocities after collision are. So you do not know V1 positive, V2 positive, or P. Right? And you have to find three numbers using two equations, and you cannot solve for three numbers using two equations. You need to generate one more equation. And the way we do this is by defining what is called a constitutive law for the colliding bodies. So we will be using what is called coefficient of restitution to generate the last equation. So this is an empirical result. That is, if two masses collide, and if let's say that the normal to the surface is in the n direction and tangent is in lambda direction. So this is perpendicular. The n is perpendicular to the line of contact, sorry, the point of contact, and passes the center of those bodies. Then we can write v1, the velocity of separation, started with n should be equal to minus e times b1 negative minus b2 negative started with n. Okay, so this, I'm sure you saw this same equation in 1D, wherein we had everything in one dimension, so you never had to deal with this ends. But now we have a two-dimensional motion, and what this equation tells you is that this constitutive law is only valid in this direction. That is, well, it's valid in both dimensions, but it's telling you how the velocity changes in the direction which is normal to the line passing through, to the line passing through the center of the flow. Okay, so we have generated the third equation, and we can now do useful mechanics with these three equations. Any questions on this? Okay, so when I wrote these things down, there are a few assumptions I made. Like let me write down the assumptions. So one thing is that the impulses are all normal to the surfaces. Impulses are normal to colliding surfaces. So if you noted, in this figure, P was in a direction of n. It was not in the laminar direction. So there are no tangential impulses. There were no tangential impulses. The second assumption is, or rather an assumption that we'll be using throughout this course is, there are no simultaneous collisions. That is, when we want to talk about collisions problem, we'll take two masses, make them hit each other, calculate the velocities after collision, then take the other two masses, see what happens, and move on. We will never consider cases where one mass collides with two masses. It turns out that you need more constitutive equations to describe that situation than what we have over here. And it's not very accurate either, so we won't delve into that world. And finally, there's something which comes up from these equations is that gravity forces, spring forces, damper forces, are negligible compared to impulsive forces. So what that means is, let's say that there was gravity here, and these particles collided in the presence of a gravitational field, then the impulse is simply the collision force minus, say, mgj dt. It turns out that these forces are negligible compared to F. So F is much bigger than mg. And so you can, for all practical reasons, you can write P equals F dt. Okay? So mg cx dot kx forces will not come in the final impulse equation. Any questions on that? So since we've set up the equations of collision, so these three equations, let's try to solve some problems. But by the way, I just forgot just to mention, if you add these two equations, okay, if you just add them, you'll see that you recover the conservation of linear momentum, right? If you add these two, this will be 0, and let me just do that. add equations in star, then what you'll see is m1 v1 negative plus m2 v2 negative equals m1 v1 positive plus m2 v2 positive. Okay, and that is what is called conservation of linear momentum. Okay, so sometimes, yeah, question?
Is that after the collision? So like the normal terms, there's two combinations, right?
This?
Yeah. The normal. Okay.
Sorry. So it doesn't really matter, right? Because this is colliding, and n is that vector which passes through the center line. So it doesn't matter. N plus n minus is almost the same because we're considering that instant lasts for a very, very brief time, very, very small. Okay, so sometimes what happens is you're not interested in this quantity, right? You don't want to know what the impulse is. In this case, you can just use this equation, the constitutive law, and conservation of conservation of linear momentum to solve the problem. Okay, now the thing to note here is that, okay, so how many equations are these? How many equations can you generate from this equation I have over here? Is it one equation? How many think it's one equation? Okay, how many think it's two equations? Okay, good. So this is actually two equations. In 2D, it's two equations because these vectors have two components, x component and y component. Similarly, this one is how many equations? Is it two equations? One equation? It's one equation because, so one equation. That's because you have this dot product. Remember when you take the work done as a dot product, f dot v, that works out to be a scalar. Similarly, it's a dot product, it will work out to be a scalar. So you really have three equations in there. Even in 2D, you just had two equations. That was one, and you had just one equation. Of course, in 3D, you'll have three equations. Okay, so let's try to solve a problem using this. So the problem I have is ball falling on an inclined plane. So an inclined plane, and I drop a ball from a height h over here. Okay, so the ball drops over here and then bounces off. So I'm going to draw the normal to the surface, and after bouncing off, it travels as a projectile and hits the surface back over here. If it's dropped from A, it collides at B, and then it collides at C again. And the question is, what is, say, T? So find D in terms of H, gravity, theta, the slope of this inclined plane. What else do you need? The coefficient of revolution. So E is the coefficient of resistance between the ball and this inclined surface. Okay, is the question clear? So let's try to analyze the motion of this particle in stages. So let's try to see what happens in going from A to B. So from A to B, but before collisions, I'll put a minus sign there. So A, B, I can just use the energy conservation, right? There's no collision taking place. Let's assume that this ball has not yet collided, and I want to find the velocity here. So energy at A should be equal to energy at B, and the energy at A is mgh. Energy at B is half mvb. Let's call this VB minus, just to show that it's velocity before collision. And so VB is square root 2dx. Okay, that was pretty simple. Let's move on to the collision. Now let's see what's going on when this ball collides with the inclined plane. So let's put here collision. B minus 2B plus. Okay, so this is the normal surface. So I'll call it N. And I want to define lambda to be perpendicular to N. So the ball is hitting with a velocity in this fashion. So VB minus is the magnitude of VB times, now this is in the, let's call this I and J. Now this is actually in the minus J direction. But since I have all the equations which I had written on the board earlier in terms of n's and lambdas, let me just try to write the velocity in this coordinate frame and not in the ij frame. So let me just do that. So in order to do that, I need to find what this angle is. And so if you use geometry, you see that this is 90 minus theta, which means that this should be theta, and this should also be theta. Okay, so the velocity now can be written in this frame. So it's VB cos theta along negative n, and it's VB sine theta along lambda. Okay, and let's say that the velocity after collision is VBx along n, VBx along lambda, and VBy along n. Okay, now the goal is I need to find what VBx and VBy is, because once I know what VBx and what VBy is, I can find what the distance is, right, based on that information. So how do I get VBx and VBy? So I have two equations at my disposal. One is I can use conservation of energy. The other one is I can use the coefficient of restitution equation. Right? Now let's see what I get if I use the coefficient of restitution equation. So that says that the velocity after collision dot with n should equal velocity before collision dotted with n. What is the velocity after collision? It is simply vp x lambda plus vp by n dotted with n equals vp minus times minus cos theta n plus sine theta times lambda dotted with n. And of course, let's forget the e. Be a minus e here. Minus e. Okay, so n dotted with n gives me v by equals n dotted with lambda gives me 0, so I'm only left with vp negative cosine theta times e. So negative would be positive, so this is going to be vp minus cos theta. So I now know what the velocity is in the y direction. I still have to solve for the velocity in the x direction. I've got this. I still need that. But I have another tool with me. I know I still have one more equation that I've not used, which is the P equals mdv equation. So I'm going to set that up. Now that says that P equals m vp positive minus vp negative. And so I can expand this out and try to club things together. So I'm going to club the x coordinate together. X coordinate is in this case here, and the y coordinate. So this is going to be, so it's vb plus minus this, and if I take these together, what I get is vb by plus vp minus cos theta times n plus m that minus this x minus v minus sine theta times lambda. Now do I know something about the impulse? The impulse p can only act in this direction, right? In the n direction. So I would write that as the scalar p times n. Okay, so I've generated two equations here. And if I try to take this and dot it with n, I would get p equals this quantity, right? The n component is this. However, the lambda component should be equal to 0 because the p can only act in the n direction. So what I can do is I can find what I will take that equation and dot it with lambda. If I do that, this n dot lambda cancels out. I get this actually equal to 0. So vpx equals vp minus sine theta. Okay, so I've solved for vby, I've solved for vpx, so I know the velocity of the ball after collision. And now I just need to solve for the projectile motion. So from B positive to C. Okay, so this ball is now shot at an angle. I don't know the angle. It's definitely not theta because if you see this dvy divided by vpx is not giving you tan theta. So it's shot at some angle, but I know the velocities in both directions. This is VBX and VBY. That's lambda. This is n. So let's start with the projectile motion. So free body diagram of this mass looks as follows, but I just realized that I'm interested in finding d, and d is along the incline, and so I do not want to stick to a coordinate frame along ij, the traditional ij. So I'll try to solve this same problem in n lambda frame. That will be much simpler as it turns out. So I'm going to resolve g in two directions. One is, so this comes out to be theta. One is along n, so that's going to be g sine theta. And it's going to be g cosine theta in direction n. Okay, so if that's the free body diagram, then LMB gives me F equals L dot, and F is the external forces. They are G sine theta along lambda minus G cosine theta along n. The whole thing has to be multiplied with m. That should be equal to mx double dot plus along I plus my double dot along j. So here x and y are measured in this frame and not in the ij frame. Okay, so I think I have a problem here. So this should be mx double dot times lambda plus my double dot. Okay, so this is xy in the frame, not in the ij frame. So if I have that, then I can take this whole equation, dot it with n, get x double dot equals g sine theta. That's pretty much it. And take the same thing, dot it with lambda, and get y double dot equals minus g cosine theta. Do I have like 2 minutes? So these are the differential equations, and the initial conditions are x of 0 is 0, y of 0 is 0, x dot 0 is vbx equals what I have there is vb minus sin theta, and note that vb minus is just 2gh. This is what I calculated earlier. And y dot 0 equals vby equals ev negative cos theta, and that is e times square root 2gh cosine theta. So equations of motion, the initial conditions, I can take these equations, integrate it twice, put in this initial conditions, and then solve for t. And I don't have the time to go over all that, but you should check me on what I get over here. So I did this whole calculation, and I'm almost done. And what I got is d equals 4e e plus 1 times h sine theta. Okay, so you can check this. For example, if you put e equals 0, if e equals 0, then this ball gets just stuck onto this body, which means that the t distance covered is going to be 0. If theta is 0, then if you make theta go to 0, then this ball is just going to bounce up and down. It's not going to travel in the x direction. So t is going to be 0. So this kind of checks. Okay.